All right. Good afternoon, everyone. So welcome to our second lecture on magnetic resonance imaging of the course HST 565. So some acknowledgement I would make to thanks for the slides from different persons. Okay, so in the first lecture, Dr. Wu introduced the basic principles of AMR, especially where the AMR signals come from and what are the properties of the signals. So in this lecture, we'll discuss how to utilize the AMR physics for imaging. We'll discuss how to design all these different magnetic fields, like these radio frequency fields, the gradient fields, to encode spatial information in the received signal, and how to decode this information for image reconstruction, and how to characterize the property of the reconstructed images. So let's first do a quick review of AMR physics. First, where does this AMR signal come from? The signals of nuclei behave just like small magnets. The orientation of these magnets are random at the thermal equilibrium. As a result, the net magnetization momentum is zero without an external magnetic field. So assume there's a static uniform external magnetic field applied in the z direction. The orientation of the spins tend to align with the direction of this external magnetization field. So that is because the spins that are parallel to the external magnetic field have smaller potential energy than those anti-parallel to the field. As a result, the net magnetization momentum along this z direction is not zero anymore. It is this bulk magnetization vector that gives us the AMR signal. So as we can see here, this relationship between the bulk magnetization and the strength of external magnetic field, we have this linear relationship. So the higher the magnetic field is, the stronger or the larger this bulk magnetization will be. That's why we will build, for the MR scanner, we try to build stronger and stronger magnetic field. At this equilibrium state, this bulk magnetization vector is simply parallel to the external field, but will not only produce a very tiny static magnetic field on the top of this main external magnetic field. We cannot detect this bulk magnetization directly as it is. So what we do is we need to get help from another magnetic field to excite the AMR signal. What we call this magnetic field is a time-varying magnetic field applied in the transversal plane, and we call this magnetic field I field or radio frequency field, because the frequency of this field is usually in the range of FM radios. So the I field is only applied in a very short period of time, let's say a few milliseconds. The role of this I field is to rotate this bulk magnetization vector from this equilibrium state along this z direction to the transversal plane. And once this, so this is a relationship we have with signal excitation. Once this bulk magnetization vector is in the transversal plane, now it will generate signals that can be detected. So basically, this bulk magnetization vector will rotate around this external magnetic field at a frequency, what we call the Lamarck frequency, which is the product of this gamma gyromagnetic ratio and the strength of this external magnetic field. So it is this rotating magnetic field in the transversal plane that gives rise, generates detectable AMR signals. So This is basically the principles of AMR physics, quick review. And then let's discuss how we can use these basic principles of AMR physics to form an imaging experiment and how to decode and encode information from these signals. So let's move to the next one. So let's start from the most basic scenarios. Let's consider how to perform a 1D imaging using these principles of AMR. Let's discuss a very simple case. Let's say we have a 2-point source with a different intensity and at different locations in the x-axis. So let's see how do we design an imaging experiment to AMR experiment to do imaging. First of all, we need to get the signal. So we apply the F pulse, and then let's try to acquire data directly, see whether we can do something with it. So it turns out the received signal is the sum of these signals from these 2-point sources. They have different intensity, but they have exactly the same resonance frequency determined by the strength of main magnetic field. So as it is now, we cannot separate the signals from source A and source B from the received signal because they have exactly the same properties. So this kind of experiment cannot give us an imaging signals. Okay, so then what do we do? Well, we need help from another magnetic field, which we call the gradient field. The central idea of MR imaging is to introduce a very controlled inhomogeneous magnetic field to encode the spatial distribution information of the image object into the frequency information of the received signals. So this inhomogeneous magnetic field we talked about is called the gradient field. The gradient field is an inhomogeneous magnetic field. The Z component of such field changes linearly along a specific direction called the gradient direction. Let's say if we have the X gradient, then this magnetic field strength with this X gradient is given by 2 terms. One is the main magnetic field, which is spatially uniform, and a small term, which is the spatial location X times the strength of the gradient. So this in total give us the external magnetic field in the presence of main magnetic field and the gradient field. So what does it do? It means that the rotation or the frequency of the signal now depends on spatial locations. Here is the animation show that if we take these spins in the middle as a reference, the spins on the right will rotate faster than it is on the left. Okay, so basically by applying this small magnetic field, the resonance frequency of the signal now depends on spatial locations. So this is another example for the Y gradient. As we can see here, if we take the middle row as a reference, the spins on the top rotate faster than spins on the bottom. Okay, so it is just like what happened in the gradient in the X direction, just in a different axis. Okay, now let's see what we can do with the help of this gradient magnetic field. So now we refine our imaging experiment as this. First, we apply an F pulse, and then we apply a constant gradient field in the X direction. While this gradient is on, we acquire data. Let's see what this received signal look like. Well, the received signal is still the sum of signals from this 2-point source, but the difference here is that now this the magic is now the signals from different spatial locations now have different resonance frequency due to this gradient magnetic field. Now I just here I just drop the factor out the effect of this main external field. Okay, so in other words, if we ignore this term, the gradient magnetic field establish a one-to-one mapping between the spatial locations of the signal source and the resonance frequencies of the received signal. So now we can distinguish these two signal sources based on their frequencies. So this is basically the principles of MRI imaging. So while this is a very basic case with 2-point source, let's consider a little bit more complicated cases where we have a continuous imaging object. Well, the same principles applies, just that the sum of the contribution of signals at each voxel becomes integral. Here, this Ix is the image object function. We have a phase term where the phase changes linearly as a spatial location of x. If we discretize things, we can write this signal in a continuous form as the following discretized form. And we here we redefine this another coordinate called kx, given like this. So here this again this gamma is gyromagnetic ratio, and is N is the number of samples acquired at the ADC, and Gx is the gradient strength, and there T is the sampling period during this ADC. As we can see here, the signal can be written in a discrete Fourier transform form. Here we define this kx as a coordinates of the signal in the Fourier domain, so which we often call it as a k-space. So now in summary, we know how to perform a 1D imaging experiment. So basically, we apply half pulses to excite signal, and then we'll apply a constant gradient in one direction, and then we just simply samples the signals while the gradient turns on. The received signal is a Fourier transform of the imaging object function, and accordingly, if we apply an inverse Fourier transform to the received signal, we can reconstruct the image. We can reconstruct the image object functions. So, do we have any questions so far? Not sure how people. Well, if you have questions, you can raise hands. Okay. If not, let's move on. So now we know how to do 1D imaging. The question is, well, how do we do with 2D imaging? Well, let's see. Well, let's go ahead and perform the experiment. We know how to perform so far. Let's see how it works. Say we have a 2D imaging object, and we perform this 1D imaging experiment as we discussed before. We apply the half pulse. We apply a constant gradient field, and then we'll acquire data. Let's see how the signal look like. Well, the signal is again an integral of the image object with a linear function, a linear phase term, where the phase linearly depends on the spatial locations. And but as we can see here, we only have this phase information encoded in one direction. Here is in the x direction. As it is now, we don't have any spatial location information in the y-axis. So can we really generate an image from this? Well, the answer is not. But then the question is, what do we do so that how do we refine this imaging experiment to enable 2D imaging? Well, let's take a closer look of our signals. As we can see, let's change the order of this integral. Let's take a look at the inner integral of this equation. What does this mean? Well, physically, it means that all the spins at the same x-axis location have the same resonance frequency. And the contributions of the signals is sum of all the voxels at the same axis locations. In other words, this inner integral is actually a projection along the y-axis. So we sum all the signal contributions for the voxels at the same x location, which is just a projection along y-axis. So then what's the received signal is, the interpolation is the received signal is actually the Fourier transform of the projection along y. So now this, we have some clue on how to perform the experiment now. So if we, again, to recap, if we apply a gradient along one direction, we have the received signal is the Fourier transform of the projection along direction parallel to the gradient direction. So now the question is, how do we do 2D imaging? Well, it is pretty straightforward from here. Let's rotate this this gradient field to different angles and obtain projections along different axes. And then if we repeat this kind of experiment, we have a 2D imaging experiment. Well, how exactly to do that? So first, we instead of apply gradient only along one direction, we'll apply gradient in both the x and the y-axis, and then give based on this strength of this gradient in the x direction and the strength of the gradient in the y-axis, the synthesized or the effective gradient field has a direction with the angle theta, which is the orientation of this gradient strength, gradient field, effective gradient field with respect to the x-axis. Okay, so if we plug these things into these signal equations, again, we exchange order of integrals. We have this inner integral, which is a projection along a direction that perpendicular to the applied gradient, effective gradient direction. While physically, it's the same picture. So all these spins with for its coordinates with a projection components along this effective gradient direction with the same component, they have the same resonance frequency. And the signal, again, at this frequency component, the receives for the received signal with this same frequency component, the amplitude is the sum of all the signals along this direction. So again, this is a projection along an angle that is perpendicular to the applied gradient direction, and then the received signal is simply a Fourier transform of that projection. Okay, so this is all this the physical meaning of this mathematics equations list here. And another way to look at these things is we can just decouple this. We can still calculate the k-space coordinates with the applied gradient directions, and we can see that this k-space coordinates has this x components and y components as calculated here. And if we plot the samples in this radar direction, we'll see that it's actually the k-space samples is along a radial trajectory in the k-space. So this is direct consequences of this central slice theorem in the CT reconstruction. Okay, now we have we know how to perform a 2D imaging experiment. So basically, again, to recap, we apply first we do signal excitation with alpha pulse, and then we apply magnetic field in the x direction, in the y direction with different magnitudes, combination of amplitude, which give us a angle of this effective gradient Then we acquire data. The acquired data is actually a Fourier transform of this projection along a direction that is perpendicular to the applied gradient direction. So for image reconstruction, it is pretty straightforward. So given one acquisition at one angle, we first apply a 1D inverse Fourier transform to get back the projections. And then if we have the projections of different angles, we can apply the conventional filter bank projection to reconstruct image. So, well, this is turned out to be exactly how the first MR imaging experiment was performed. So here we show this is the paper published by Paul Lotber in 1974 in Nature, which is, he of course got the Nobel Prize because this this work, or actually 1973. Okay, well, how to perform 3D imaging? Well, it is pretty straightforward from 2D. All we need to do is apply gradient field in a third direction, in the Z direction. So if we change the combination of this gradient amplitude for the X, Y, Z directions, we get effective gradient at different directions in these 3D coordinates, which translate to a radial trajectory in the 3D K-space. And then if we rotate these gradient directions to cover this entire 3D space, and then we get image reconstruct. So here we covered so far how to do how to perform imaging using MR, only use constant gradient strength. So what else we can do? Well, let's revisit our 1D imaging experiment. So in the previous imaging formulation, we use the frequency information of the received signal for spatial encoding. What can we do differently? Well, if we are talking about the frequency of this signal, it is natural to think of the phase of the signal. So we can distinguish the time domain signal either based on their frequency or based on their phase, or a combination of both. So then the question is, can we redesign this 1D imaging experiment instead of encoding the spatial information into the frequency of the signal? Can we think of a way to encode the spatial information of the signal into the phase of the received signal? Well, the answer is yes, and the experiment is performed this way. So first we apply half pulse to excite signal, and then after this half pulses, instead of applying a constant gradient field, we apply a time varying gradient field. More specifically, we apply a gradient field only lasts for a short period of time, and then right after this gradient field is gone, we acquire one sample. Okay, so that's the difference. So number one, we instead of apply a constant gradient, we apply a time varying gradient, a short gradient pulses lasts for a few milliseconds, and then we acquire one data samples right after this gradient pulse. Okay, let's look at the signal, how the signal looks like. Well, again, the signal from these 2-point sources now have different phase now, because while the gradient they turned on, this point sources here and here, they rotate at different frequency, which accumulate different phases, amount of phase with this same period of time. So now this signal, the spatial location information actually is embedded in the phase information of the received signal. Of course, we cannot distinguish these two signals based on only one samples, but if we repeat this experiment many times with different gradient pulse strings, now we can distinguish these two signals. Well, so how to mathematically, Well, let's consider a more general case. Let's assume the image object is a continuous function. And if we perform this kind of experiment, the received signal, again, has a Fourier transform relationship with the image object function. Here, this fixed term now depends, is also a linear function of spatial locations. So the same image reconstruction formulation will apply. The received signal is a Fourier transform of the image object. To do the image reconstruction, we simply need to do inverse Fourier transform. So, well, now we have two ways to do a 1D imaging experiment. Let's do a quick comparison, see what's the pros and cons for each method. Let's say for the method on the left, we'll require one measurement for imaging, for 1D imaging, where the sample signals are acquired when a constant gradient is applied. The spatial information of the image object is encoded into the frequency information of the received signal. There's a Fourier transform relationship between the image object and the received signal. Well, for the method on the right, we perform multiple measurements for 1D imaging. In each measurement, a short gradient pulse with different amplitude is applied after the signal is excited, but before the data acquisition. And for each experiment, we only require one sample. The spatial information of the image object is encoded in the phase information of the received signal. However, it turned out to be we have the same Fourier transform relationship between the received signal and the image object. So for 2D imaging, for 1D imaging, of course, this frequency encoding approach on the left is desired because we only need to perform one experiment to acquire all the information we need to perform image reconstruction. Well, for this phase encoding approach, we need to repeat this experiment many, many times so that we have enough data to perform image reconstruction. However, this phase encoding approach turned out to be very useful to design multidimensional imaging experiment. For example, if we want to do a 2D imaging experiment, we can use combine this frequency encoding with a phase encoding. More specifically, after the signal excitation, we apply this short gradient pulses in the y direction so that we can encode the spatial information along the y-axis into the phase information of the received signal. And after that, we apply a constant gradient in the x-axis so that the signals acquired during this gradient is turned on, the spatial information along the x-axis is encoded to the frequency information of the received signal. The received signal for the total experiment again has a Fourier transform relationship with the imaging object. Here, that the only difference from the previous 2D imaging experiment is that now we sample the data in the K-space on Cartesian grid. Well, extend this idea to 3D imaging is very straightforward. We just apply another gradient field in the z direction with different amplitudes for each measurement. So basically, we encode the spatial information along the y and z axis to the phase of the received signal, and encode the spatial location along the x-axis to the frequency of the received signal, and it turned out lead to a Cartesian sampling in the 3D K-space, and then the same Fourier transform relationship exists, and the same image reconstruction method can be applied. So now we talk about this K-space a lot, and we talk about different sampling trajectories in the K-space. But how do we? So what is a K-space? So what is the property of the K-space? Well, let's take some quick examples. to have a sense. The K-space, again, is basically the Fourier transform domain of the image object. And our data, MR raw data, is sampled in the K-space as discrete points. So very quickly, we can imagine we have two issues when we're talking about how to sample the K-space. One is how densely should we sample the K-space. The other is to what extent we should sample the K-space. Well, for the first question, the images on the top show the case that when we have proper sampled K-space with proper density, and then we have this image reconstructed shown on the right. However, if we skip lines, all these dashed lines here in this top row and only sample the solid lines in the bottom row, and then we end up images with aliasing. As you can see that the images on the top part is aliasing back, the bottom part aliasing back to the top, and vice versa for the bottom. So clearly, it looks like the sampling density of the K-space is related to aliasing of the image. Well, how about the range of the K-space? Well, this is another experiment. So we have a large K-space coverage in the top row, and we get images with high spatial resolution. And if only sampled images only half of it, and then we get a very blurred image. Okay, so clearly when we design an imaging experiment, we need to determine how densely we should sample the data and to what extent we should sample the data. Okay, so that translates to our 2D imaging experiment, which is how to determine all these imaging parameters. For example, if for the phase encoding gradient, how big or how strong the gradient strength is, given this duration of the gradient, how many steps we need for the phase encoding. For the frequency encoding directions, it's the same question, how strong this gradient strength should be, how fast should we sample the data in this direction. If we translate all these parameters into the K-space, we're talking about what's the sampling density in the K-space, in the X direction, in the Y direction, and what's the K-space coverage should be. Okay, so then let's discuss how to answer these questions. The first question is sampling density. Well, the mathematical principles here is actually the Nyquist sampling theorem. Okay, so to recap, for the Nyquist sampling theorem, what we say is given a signal that is band limited in the frequency domain. In the time domain, we only need to sample the signal as at a sampling period that is smaller than 1 over the bandwidth of the signal. Okay, so in MR, it is exactly the same thing. Let's say we have an imaging object in the 1D case with limited spatial support. Here we call the field of view. And so this is signal intensities equations. And then we apply, for the frequency encoding, we apply a constant linear gradient so that now we map this this image object as a function of spatial locations, now as a frequency distribution, as a function of frequency. Now the bandwidth, the spatial support of the image object or the field of view is translated to the bandwidth of this frequency distribution, which is given by this field of view and the applied gradient strength. Well, and then when we sample this data in the frequency encoding direction, we just need to determine the sampling period, which is given by the Nyquist sampling theorem, which is 1 over the bandwidth of the signal. So if you plug all this math into to perform the calculation, we can get the following relationship about given the field of view of an imaging object and the gradient strength that we applied for the frequency encoding, what the sampling period should be. Or when we talk about things in the K-space, the sampling density in the k-space in the frequency encoding directions, delta kx, should be less than 1 over field of view. Okay, so this is how we determine the sampling density in the frequency encoding directions. It turned out to be, we can apply the same principle for the sampling density along these phase encoding directions. So here we get the requirement for the k-space sampling as a transition case for both the along the kx direction, which is the frequency encoding direction, and the ky direction, which is phase encoding direction. And given the relationship between delta kx and delta ky, and we can calculate the relationship between the gradient strength, sampling period, or the given the phase encoding durations, what's the step size of this phase encoding gradient. Okay, so now let's move to the next topic, which is the k-space coverage. So the question we want to answer is to what extent we should sample the k-space. Well, the answer lies in the answer about the characterization of the resolution of the image. So here we show two examples. One low resolution image from on the left and one high resolution image on the right. So as we can see clearly, these two images has a different resolution. But another thing is the image on the left not only have low resolution, but also have a lot of kind of ring artifacts. Okay, to make it more obvious, we change the window width and the window level. And here we can see these ring artifacts more clearly. So how do we explain these things? How do we characterize both the resolution and also explain the ring artifacts? Okay, so the mathematical tools we use is so-called the point spread function. Let's consider a point source in the image domain. And the point source mathematically is defined as a Dirac delta function. So it is 0 unless for x equal to 0, the integral of this function is 1 and some other mathematical properties. The most important property for the context of MR is if we perform Fourier transform to the point spread to the point source, the resultant k-space signal is constant. It is 1 all over the k-space. Now let's say we have in total n samples of this point source. They are all equal to 1, and then we perform a Fourier transform on this k-space data, which is writing like this. So the signal intensity is always 1, and then this is inverse Fourier transform coefficients. We end up with a closed form solution for the Fourier reconstructions of this point source in the image domain with uniform sampling and in total of n number of samples. So this reconstruct image is called a point spread function. And for this special case, we have this, has a form of periodic sinc function. Okay, so this is the plot of this reconstruct image or this periodic sinc function. Immediately we can see that instead of a point source in the image domain, now the reconstruct image has some width in this, as we can tell as a main lobe. And besides this main lobe with finite width, we also have these side lobes, and the intensity of these side lobes kind of decay gradually as they move further and further away from this location of this point source. So it turned out to be, it is the width of this main lobe explains the resolution of our reconstruct image. It is the side lobes that give us that ring artifacts. Okay, for more specifically, let's consider 2 point sources. One is green, one is red, and then we can calculate the point source, the point spread functions of these 2 sources, and we can see that they overlap. And we define the resolution of this reconstruct image as it is using this so-called full width at half maximum formulation. And then if we plug in this point source function and calculate resolution, it turns out to be this resolution has a very simple relationship with the field of view and the number of samples, which is this resolution is basically the field of view over the number of samples. So in some sense, it is very intuitive. Okay, so, but this is the mathematical characterization of the resolution of reconstructed image. Here is some numerical examples. Here we plot the point spread functions with different number of encodings from 64 encodings, all samples, all the way to 512. As we can see, the main lobe width is getting narrower and narrower, and the side lobes, although the maximum intensity is almost the same, but the distance between the first side lobe and the main lobe is getting smaller and smaller for this as this number of samples increase. So while here's this representative image reconstructions with different number of samples, and as we can see here, this is one has the highest resolution, this one has lowest resolution, not just blurring, but also very noticeable ring artifacts. And then when we increase the number of samples from 64 to 128, the resolution improves and the ring became less noticeable, and we have pretty good image qualities at 256 encodings. Okay, so this is how we characterize image, the resolution and the ring artifacts. Okay, now we know another set of parameters regarding the K-space sampling. Basically, it is the coverage of the K-space, which is determined by the desired resolution. Okay, so the number of samples is a field of view divided by the number of the desired resolution in both X and Y directions. Okay, now to this end, we have accomplished this, this loop. Now we know, given an image object, we know how to design a 2D imaging experiment or 3D imaging experiment to acquire this MR data. We know how to specify all these imaging parameters of this so-called MR sequences. We know how to determine the field strengths, how many steps we should do to perform each frequency encodings, and how many samples we should acquire in the frequency encoding directions, and how many samples we should acquire in the frequency encoding direction and also in the phase encoding direction. Okay, so but very often that is not enough. We have this this imaging experiment usually tend to last very long. So the question, a very hot topic in the current MR research is about how to accelerate the imaging speed. Okay, so let's see what can we do to acquire data more efficiently. Okay, so while let's put this image acquisition time into context. So we usually repeat for this 2D imaging experiment, we need to repeat multiple times to acquire this full set of data for image reconstruction. For the sake of contrast, we often, there's certain period of time that we need to wait so that to build the contrast. As a result, we have this so-called repetition time between measurement. So the total imaging time will be the total number of samples in the phase encoding directions times this repetition time, or TR. Then the question is, how do we reduce the acquisition time? Well, the first idea here is, as we can see that the imaging experiment we discussed so far, we only acquire one K-space lines per repetition time. So very naturally, we are wondering, well, do we have to do that? Can we acquire multiple K-space lines in one repetition time? Or can we even acquire all the k-space data, all the k-space lines in one repetition time? Well, from the imaging sequence perspective, it's that instead of we'll have multiple phase encoding gradients applied, and and in between we have this frequency encoding gradient in the oscillating fashion. So in the k-space, we acquire k-space lines from right to left, and then jump to another k-space location in the y direction, and then acquire frequency encoding data from left to right, and so on and so forth. So actually, if you're aggressive, you can acquire the entire k-space in this fashion using one repetition time. So by doing this, we can significantly reduce the number of the acquisition time for MR. So this is the so-called this echoplanar imaging sequence, and which is widely used in current MR studies, especially in function MR. And of course, this is the image. This idea is first proposed by Sir Peter Mansfield, who also got the Nobel Prize for the discovery of MR, shared with Paul Loutberg. So what else can we do? Well, so this is the spin echo sequence that we didn't touch, but the idea is we have two alpha pulses for each signal excitation, but to get proper SNR, we need to wait for a long time before we repeat this alpha pulse excitation. Okay, so, and well, how to accelerate imaging speed in this scenario? Well, the idea is, again, let's acquire multiple k-space data along multiple lines for within the same repetition time. So the idea here is we apply multiple 180-degree pulses, and then we can recover signals at the T2 decay. And between these 180-degree pulses, we'll apply different phase encoding gradients so that we can sample k-space data at different k-space locations in the phase encoding direction, and then we apply gradient, the same gradient field at different echo times, so that we have multiple echoes. Each echoes have different k-space encodings. So by doing this, we can also significantly accelerate the imaging speed. So this technique is called fast spin echo sequence. So this fast spin echo sequence is probably the most widely used sequence in the clinical MRI. So again, the idea is pretty much similar as this echoplanar imaging. So instead of acquire just one k-space lines per repetition time, let's try to design gradient and alpha field so that we can acquire multiple k-space lines per repetition time. Okay, so the next idea on accelerating imaging speed is to acquire less data. So again, this is a picture we saw when we talked about k-space sampling, as we know that if we don't sample the k-space data at density small enough, we'll have this aliasing in the image, which cannot be resolved without additional information. Well, it turned out to be, we do have a lot of additional information we can take care of, we can take advantage of. This is one of another very popular examples, which is called phase array coils. So the idea is we have coils at different position around the image object, and each coil have different sensitivity information that is known in advance. The sensitivity information shown here is basically very intuitively, if the voxels close to the coil, we have higher sensitivity of receiving, so the image looks like bright. And for the voxels that is far away from the coil, it looks dark. The important thing is different coil have different sensitivity patterns that we can take advantage of, and we can measure it in advance. Now, so this is images with fully sampled data. And this is images that we acquired with only half of this sampling. Basically, we cover the same K-space range, but at less, with a larger gap. So as a result, we have aliasings from these different positions of this image. So the idea here is that for this aliasing voxels, we know exactly how this voxel is aliased. For example, for this voxel at here, it is the alias, so the signal from this voxel is the sum of the voxel here, which is in the alias image, and the voxel that is alias in the alias image at this position. Okay, for different coils, since we know the coil sensitivity information, so we know that the reconstruct image for the first coil is actually the sum of these images, an alias image with template multiplied by the coil sensitivity at this position, plus the alias voxels at this position with the corresponding sensitivity maps. And similarly, we have equations for the second coil. The important thing is for the coil 1 and coil 2, there is a different sensitivity information that is known, and they are different. So now we have two unknowns, which is the original, the alias image at this voxel and the alias image at this voxel. And we have two equations, and this C1, C2 is, can be measured in advance. By solving this linear system, we can recover both the alias image as this voxel and the alias image as this voxel, so that we resolve these aliasing artifacts as we see in this image. So this is a basic principle of parallel imaging, which is also very widely used in current MR scanners for accelerated imaging speed, for accelerated MR data acquisition. Okay, so in summary, we talked about some, we didn't, this is what we have covered. We covered the basic concept of MR imaging, the NMR physics. I think also in Dr. Wu's lecture last week, we covered the contrast mechanism. And then in this lecture, we focus on specifically on the K-space and K-space sampling. And we on, for example, how to design a 2D or 3D or 1D imaging experiment with different K-space sampling schemes, and how to perform image reconstruction with the acquired data, and how to sample the K-space for different trajectories, and how to characterize the reconstructed image property. On the top of this, we discussed several schemes for fast imaging, basically how to acquire multiple K-space lines in one repetition time, and how to unsample the K-space, but still recover the images without aliasing with the help of coil sensitivity. So, well, so this is an example of speech imaging. As the music you heard is this guy is singing this music while in the MR scanner. And this is how these vocal structures change as this guy is singing in the MR scanner. And this is just examples of what MR can do. So basically, what we see is there's nothing that the nuclear spins will not do for you, as long as you treat them as human beings. So there's very rich information that we can extract from MR signals, from the spectrum information, diffusion information, different changes, and all the way to this dynamic imagings, cardiac imaging and dynamic speech imagings. Well, so I think that will be the end of this today's lecture. And I think we have times for questions if there are any.